This is a summary of what we've learned about the behavior of these four elements in a circuit: a battery, a resistor, a capacitor, and an inductor, meaning a coil or a solenoid. So suppose we define the direction of the flow of positive current to be to the right. That's all important. That's choosing your axes, choosing your directions. So to the right, a current flowing to the right, let's call that a positive current. And then if we have these circuit elements lined up along a wire, we can write down an expression for the potential difference that we encounter as we move from left to right across each one of those elements. So our potential difference as we go from left to right, meaning V final minus V initial, V final on the right-hand side of the element minus V initial on the left-hand side of the element. Okay, so if we have a battery oriented this way and we're going this direction through it, we're going from the negative terminal to the positive terminal. That's the high potential side, that's the low potential side, so we're going up in potential plus the EMF. If we're going with positive current through a resistor, then we're going down in potential. It's a potential drop if we're going with positive current, so minus IR as we go in that direction across our resistor. Then we hit a capacitor. We have to define a Q to be the charge on one particular plate. So if we define Q to be the charge on the left-hand plate here, then if current is positive, it is going to be adding positive charge onto this left-hand plate. So a positive current will be increasing the charge on that left-hand plate. We can write I equals dq dt. Positive current increases the charge on this particular plate. So if we make those choices, then as we move from left to right across that object, we're going to be going, our potential difference can be expressed as minus Q over C. So V final over here, V at this plate, minus V initial at that plate will be minus Q over C. So if Q is positive, then we're going down in potential as we go to the right. If Q happens to be negative, if we have negative charge on this plate, Q is negative, that negative sign indicates that as we go from left to right, we'd actually be going up in potential. So this expression works whether Q is positive or negative, as long as we've defined Q and I to be related this way. So if a positive I increases Q, then this expression tells us the delta V as we go from left to right. Okay, and then lastly, our inductor, our coil, our solenoid over here, this spring-looking symbol. Minus L di dt is our potential difference as we go from left to right across that. So V final, V at the right, minus V initial on the left gives us this. So if we have a positive current this way that was increasing, then di dt would be positive and our potential difference would be negative. So if I was positive and increasing, this would be behaving like a battery pointing that way. We'd have a negative EMF, so we'd be dropping in potential as we went across it. If, on the other hand, I was positive but decreasing, so di dt was negative, then negative times negative makes positive, and we'd be going up in potential as we went from left to right. This inductor would be behaving like a battery pointing to the right, in that case trying to boost the current to keep it going. Okay, so I'm saying these expressions here work for current going in either direction, for a positive current or for a negative current, as long as we've picked the direction for positive current, and they also work for current increasing or decreasing. All right, so with those conventions, let's have a look at what happens in a circuit when you flip a switch and change the possible paths for current to flow. So suppose we've initially got some current in an equilibrium state. We have some capacitor or multiple capacitors in that circuit and some inductors in that circuit. So suppose in our initial steady state, we've got some charge Q naught on a capacitor and some current I naught flowing through some inductor. Then we throw a switch. So what changes right away and what changes if we wait a really long time? So what happens just after the switch is thrown in your conductor and in your capacitor and your inductor, and what happens a long time later as t goes to infinity in your capacitor and in your inductor. So just after the switch is thrown, Q prime will be the charge on the capacitor. Just after the switch is thrown, I prime will be the current through your inductor just after that switch is thrown. And the point here is that the charge on the capacitor just after throwing the switch is equal to the charge on the capacitor just before throwing the switch. It cannot change instantly. It takes time to add or remove charge from a capacitor. So if you instantly throw a switch, the charge hasn't changed yet. That's going to take some time. Similarly, through an inductor, the current through an inductor just after you throw a switch will be equal to the current through that inductor just before you throw the switch. It takes time to change the current through an inductor. That's an inertia-like effect that an inductor has. You can't change that current right away. It's got to evolve over time. So let's wait a really long time. If we wait for t to go to infinity, then the charge on our capacitor will eventually approach some final constant value. Maybe zero, maybe non-zero, but it's going to approach some final constant value. In that case, the current through the branch that the conductor is on, the branch that the capacitor is on, the current through that branch will be related to the rate of change of charge on the capacitor. So if that charge is approaching a constant, some final constant value, then dq dt is approaching zero. In other words, the current delivering charge to that capacitor has to go to zero if we wait a really long time so that charge can approach its final constant value. A capacitor branch goes dead in the sense that eventually current stops flowing through it if we wait long enough. That's the long-term behavior of a capacitor. No more current flowing through it. An inductor, on the other hand, if we wait a really long time, the current flowing through that inductor may have changed from what it was initially, but it will approach some final constant value. Maybe zero, maybe non-zero, but the current through that inductor will approach some final constant value, meaning that the potential difference across that inductor, your EMF here, related to the rate of change of the current, well, if the current is approaching a constant, then di dt is approaching zero, the EMF approaches zero. If we wait a really long time, there will be no potential difference across any inductor in your circuit. No EMF across it anymore. Basically, if you wait a long time, your inductor eventually behaves just like a wire, allowing current, a constant steady current, to flow freely through it without any potential difference there at all.